All right, let's get started. All right, our first homework is posted, okay? So if you go into Canvas, so under week 2, you will see actually 2 links, okay? So there will be like one homework for the 4502, so that's the undergraduate section, and also 5502, so that's the graduate section. Make sure you submit to the correct one, okay? Because the grading is different at the set, like undergraduate section, graduate section, we have different like grading. Some of those are the same, some of those will be different. So make sure this one, click the right one, okay? Deadline, so usually what we do is I will post before Thursday's class, and it's due before Thursday's class. So you basically get 1 week, all right? So make sure you check check Canvas, check out the homework, start working on it soon, okay? So this one, we actually have a Python programming work for question 3, okay? So that one, if you haven't used a Jupyter Notebook before, so there are some like instructions in the homework, and there's actually CS has online like a Jupyter app that you can use, so you don't have to set up your own environment. You can, but you don't have to, okay? So if you have any questions, of course, like come to our office hours, okay? So if you haven't checked it already, go into Canvas under syllabus. We have posted our office hours, okay? So today is Thursday. I had my office hour just before this class. And then Monday, Tuesday, Wednesday, we have 3 more sessions of office hours, okay? Me and the 2 other TAs, okay? So those are the office hours that you can come in, ask specific questions. Outside that time, like if you need to talk to any of us, schedule a meeting, so please contact us to schedule a meeting, or Piazza, okay? That's where you can also ask questions, and the class can help each other, and we'll try to respond quickly. We are there, okay? So those are basic things. Yeah, check out the homework. Start working on it soon. You have questions. One, you can check our lecture slides, the lecture recordings. These are all in Canvas, okay? And then come to our office hours, ask questions in Piazza, okay? All right, so first homework, start working on that soon. All right, so starting in Tuesday, back in Tuesday, we started talking about the very beginning of data mining, right? So chapter 1 was really just the intro, right? Generally talking about data mining. Chapter 2, we now started doing some concrete work, okay? So the title has like data measurements and the data pre-processing. We kind of covered the data and the measurements aspect. So this is more about understanding your data, right? So at this point, we haven't changed anything, right? We get the raw data, okay? Start like looking at the raw data, trying to get some ideas about what the data look like, but we haven't done anything in terms of changing things, okay? Pre-processing, that's when you start modifying, okay? So we stopped at the similarity and the distance measurements, so we have a few slides that we need to finish from that section, okay? So remember at the very end of the previous lecture, we were talking about how you measure, right, similarity, distance, because this is really the core concept in terms of data mining, right? We're looking for similar things, we're trying to differentiate things. So the basic notion is that given the object being described by certain attributes with specific attribute values, right? How do you determine how similar or how different 2 objects are, right? Okay, so since there are different types of attributes, okay, so we say like if it's like a nominal data, then you really are checking matches, right? Whether they're exact match or not, okay? Binary variable, similarly, you can say whether it's they're both 1s or both 0s, right? But there's a slight complexity here, okay? So typically when you have symmetric binary variables, okay, so all we're talking about is that when they're different compared to the overall scenarios, right? Because when you have 2 binary variables here, right, A and B, A can be either 1 or 0, B can be either 1 or 0. So these are the 4 possible cases, right, of the A and B values, okay? So if you count the total instances in each of those scenarios, right, Q, R, S, T, then that's the total number of instances, and out of that, R and S represent when they're different, right? So if you're calculating like how different 2 objects are giving their binary variable representations, then you're basically counting how many times they're different, right? So if you say, if you take 2 students, right, each student lists, okay, these are the courses I've taken, or I have taken these courses, or I have not taken this course, right? So you basically get this binary vector, right, 0 or 1, corresponding to each course they have taken, right? Okay, so now you're just counting how many courses they both have taken, how many courses they didn't, like one took, the other didn't. So that's how you're calculating the differences, right? Okay, so in the symmetric case, right, so this is when we say there's roughly equal chance of the variable value being 0 or 1, okay? So if you say out of all the CS courses, it's yeah, there's maybe half chance, or roughly half. If you talk about the gender, half. If you're talking about graduate program versus undergraduate, maybe half, roughly, right? As long as they're comparable, okay? So in those cases, we count R plus S, that's these 2 cases, and then we have all the 4 scenarios being the denominator, right? So out of the other possible scenarios, how often they're different, okay? But in many real-world scenarios, your variables, the binary variables, are not symmetric, okay? So I was using this example, say if you go into Amazon, right, and you're trying to buy products there, okay? So Amazon's online platform, they sell a lot of things, okay? So let's say 1 million. They have 1 million products, okay? And if you take any 2 customers, and then you're trying to measure how similar, how different they are based on the things they have purchased on Amazon, okay? How many you have purchased? I have purchased probably hundreds of items there. A little bit more maybe, but it's far from this 1 million number, okay? Another customer, possibly still maybe around 100, even maybe a little more thousands, but that's about it, right? So it's unlikely that when you're comparing these 2 customers, they would have covered this 1 million possible products, okay? So in those scenarios, now you think about your QRST, right? Q is probably, okay, if you say, I have purchased hundreds of items, the other customer has 100 items, so maybe we have both purchased maybe tens. Similar, if we're really similar, we may have, say, maybe hundreds that are similar. I mean, we purchased the same item, okay? But the tricky part is this T. T is basically the 0-0 scenario, right? I didn't purchase it, and the other customer didn't purchase it. And that is actually out of the 1 million, it's probably a very big number, close to 1 million, okay? So now if you count T in, if you're still using this formula, what would you get? So basically that T will be dominating everything, right? So you get a number that's very close to 0. So that's really not meaningful, right? So whenever you take 2 customers, if you calculate using the current calculation, it's always 0, meaning that they're very similar. Distance is almost 0. But that's not really what we want, right? Because we care less about the millions of items that we didn't purchase. It's more about out of ones that we did purchase, right? How similar, how different things are, okay? So that's the key notion about the symmetric piece or this asymmetric. So that's the other one. So when you have asymmetric variables, meaning that for this particular variable, it's much more likely for one value to happen than the other, okay? And when you have that, then you want to use this formula, which basically just ignores this T, okay? Ignore the 0 cases, 0-0 cases, okay? And focus on the ones that at least one of us did something. Make sense? Okay? So mathematically, we say if you have a T that's too big, that would really throw off your calculations. It's not good. But semantically, we just don't care as much about those 0-0 cases. Okay? All right, so with that, right, so that's my new calculation, and then this also referred to as the Jacob coefficient. So this is for similarity. So you're basically, again, looking at how similar. So Q is the ones when they're similar. So say if you don't want to look at what kind of movies people like, right? So you maybe look at the Jacob similarity, just, okay, how many movies both of you liked, both of you have watched, right? Versus the total number of movies that any of you have watched. Make sense? Again, I care less about the many other movies that none of us watched. Okay? All right, so that's the notion about binary variable, okay? We're still counting when they're similar, when they're different, but the one key notion is about whether we include or exclude the T cases, okay? All right, so then my last slide from last lecture was that we're using this example, right? So note here, right, we're basically saying we have 3, right, people, okay, patients or whatever, right? So they come in, they have some symptoms, we did some tests, and then we're basically trying to figure out which patients have similar, like, symptoms or test results. Question? Sure. Oops. Yeah.
You're saying we ignore T if the value of T is greater, right?
We include the T when T is meaningful, meaning that, so like for symmetrical binaries, I care about the cases of T when it's 0, 0, meaning that none of us watch it, but like say if it's courses, right? Like this is CS course, I expect like half of the student would take it. So the fact that you didn't take that course means, like, or none of you take that course means something that I want to include, okay? But if it's about, like, if a T is about, say, like, out of a huge number of instances, and we're just checking whether, say, you purchased the same thing, then that T, like, I care in a way, just like, if there's 1 million items you could purchase, it's not that important that none of us purchased those items. Make sense? Okay? So that's the reasoning, right? So it's basically just say, do you, like, as I said, like, mathematically, if T is too big, the calculation is not meaningful, so you probably want to, it wouldn't help you anyway. But semantically, it's like, why do we want to include or exclude T? That's because I care, or this doesn't matter, or not as much in my calculations. Make sense? Okay. All right. Now, with that, right, so if you have this actual calculation, like numbers, say I have 3 patients, I want to basically measure how similar or different they are, right? So in this case, I have gender, which is a binary variable, but it's symmetric. But the others, right, having fever or not, coughing or not, right, and your test results being positive or negative, that usually is asymmetric, because if you take any random person come in, do a test, and like how likely you get a like positive, right, or negative answer, right? So if it's like some kind of like a cancer thing, then you say, okay, yeah, it's a much lower chance that someone will come in with a test result that's positive for a particular indicator of cancer. Okay, so knowing that though all the others are asymmetric variables, so we're using this calculation, right, without the T, okay? So basically what we do is that we calculate, we count, right, how often they are different. So one's, let's say 1, 0, or 0, 1, or positive, negative, negative, positive. So those are the RS cases when they're different, right? And then we also need to count this Q. Q is when they're both positive. Okay, right? So if you did this calculation after class, okay, those would be the numbers you get. But basically, we're just counting the instances, right? Let's do this one, Jim and Mary, okay? So Jim and Mary, we will look at R and S, okay? So that's basically when they are different, okay? So this NP is one scenario, PN, PN. So that's why I have 1 of the NP case, 2 of the PN case, right? That's my nominator. Okay, and then I will add in Q. Q is when they're both true, so that's the 1, 1 case, right? YY, that's for fever. Okay, so I have 1 for Q. So if you add this all together, you get your calculated like distance. Okay, so we'll be just counting, right? How often they're different, divided by like the total number of cases when they have at least 1. Okay, so this is binary. Okay. Ordinal. Okay, ordinal basically say, okay, these are still kind of like fixed numbers, but they have some kind of order, right? So if you just take undergrad, let's say like your bachelor degree, master's degree, PhD, or you take like professors, assistant professor, associate professor, full professor, those are just ranks, right? So to calculate the distance or similarity, you basically assign some kind of numerical value. So they can observe the order, right? And then you can calculate how similar or how close they are, right? So basically what we do is that we just map it, right? Map to the ranks, map to the range of 0 to 1. So if you have, let's say, m different ranks, all you're doing is basically just divide it up so that you kind of have these values in between, right? Okay, once you have that, right, so in this case, like if you say it's only 3 ranks, right? Gold, silver, bronze, then they can do 1, 2, 3. And then you can see apparently like gold is further away from bronze, but like silver is kind of in between. So you have a way of measuring the like how different or how similar things are. Okay, all right. One more. Variables and mixed types. Okay, so what is that, right? The second V when we talk about the data is about like a variety. So that means you have different types of data. Okay, so most of the times when you're working with data sets, when you look at the attributes, right, they are of different types. Okay, and because they have different types, apparently you need to treat them differently, even though you need to aggregate, like look at the combined similarity or difference. Okay, again, see, if I'm comparing two students, the student can have like numerical values in terms of age or maybe in terms of score in particular courses, but like also have other like nominal information or binary information in terms of like their gender, which courses they have taken, which major like degree program they're in. So you have a mixture, right, of the different types of attributes, okay? So ultimately, we want to be able to take all this together and combine it, okay? So just know that as you're looking at your data, looking at your attributes, you need to do your reasoning, right, about how you want to combine those different attributes, okay? So the formula is actually like simple, right? All you need to determine is how to calculate the individual ones, right? So if you know like there are like certain number of features, you go through those features. For the individual features, you have a way of defining their different like distance function, and then you combine it, right? Okay. But when you combine it, also, of course, there are ways for you to determine, like if it's 0, like if you say, I had a value here, and you don't have a value, apparently you cannot do that. So there's some like 0 scenarios. You can also add weights, right? For example, like I think there are like, say, which degree program they're in is more important than the individual scores they get in a particular course, right? Again, those are a lot of domain knowledge you can leverage, right? So that's why it makes sense to understand your data, understand your attributes, do some statistical analysis of your attribute values, right? And so when you combine this together, you have some way of saying why I'm doing it this way, or why I'm ignoring those like fields or those attributes because they're not useful, or I'm ignoring certain extreme values because they're like noise or like errors or outliers that I don't care about. Okay, so all this go into the reasoning for you to be able to come up with a way to combine across attributes. Okay, I'll give you one more example. Okay, so we talk about like nominal, like ordinal, binary, and numeric cosine similarity. This is about documents, right? So for any of you who have like worked with like documents or text data, right? So typically we say I have many documents. I'm trying to figure out whether they're similar or how similar things are. Right, so many times we use this what we call like keywords or tokens that basically just say the main information in the documents, okay? And we use this frequency count, okay? So you may have worked with, like, say, a way of, say, representing the documents. Like for different documents, what you do is basically go through the documents, trying to look for certain keywords, and then you count. So 5, 3, those are all frequencies, like how many times you have seen a particular keyword, right? So based on the combined like frequencies of those keywords, then you have some idea about what they're talking about, right? Those documents. And now you have a way of measuring the similarity. Okay, so using cosine similarity, what do we, it's not my phone, but somehow this keeps ringing with messages. Okay, so what we're basically doing is that we take this, these are vectors, right? Those are like basically like the word vectors, okay? Okay, so you're basically doing this, this one out. Okay, so if you have one example, so what I do is that I take x and y. X and y are the two different vectors representing two different documents, right? Okay, so this is the transpose so that you can, well, they would have the same number of dimensions, and then you do the normalization based on the scale of x and y individually. Okay, so if you do the calculation, right, in this case, what you do is you take the corresponding dimensions, right, multiplying the frequency values, add them up, and then you need to like divide by the, like scale it down, so that's the value you get. And with that, then you have a way of like comparing, okay? So for example, like D1 is this, D2 is this, so I have my cosine. So this is the similarity between document 1 and the document 2, okay? One quick question, is this one symmetric? Meaning if I'm comparing D1 and D2 versus D2 and D1, do I have the same value or not? Yes, okay? So this is so that's always talking about like whether like say if you switch the order, are they still the same, right? So in this case, I have D1, D2. You'll see this is a one value, and now if you want to compare maybe D1 with another document, you get another cosine similarity function value, and then you can compare which ones are more similar. Okay, so that's good. This actually has been shown to be very useful, like with all the search engines, a lot of the like text analysis, right? Cosine similarity is a very useful way to identify documents that are similar versus dissimilar. Now let's look at this example. Okay, oops. Sometimes too sensitive. Okay. Gee. Okay, I hope you got a glimpse of that phrase. What do you see here? All right, so I'm showing you two short phrases. If you use the document, like the word frequency, they'll be exactly the same, right? And your similarity calculation will be the same. But apparently, they mean different things, right? Okay? So again, this is just a quick example, but you see, that's why I say you cannot just take one distance function and be done with it. Sorry, it's not that easy, right? So you need to understand what you're trying to do and get into some of the specifics. So they're basically just saying like there are some kind of semantics that are just not captured by the cosine similarity calculation or the way I'm representing the attributes, right? Okay, so we'll be talking about it later. So that's why it's a challenge to not solve the problem, right? We still actually have a long way to go in sort of better understanding of text data or other types of data, okay? But keep that in mind, okay? So as you're working with different types of data, look at the attribute values, look at the distance functions, try to do your reasoning. Is this sufficient for my problem? Or there are actually things that are not or there are some gaps or challenges that need to be addressed further. All right, so I'll talk about one more. So this one's called KL divergence, okay? Kullback-Leibler divergence. Some of you may have heard of this. If not, you can look it up. But general idea here is that I'm looking at two distributions, okay? And I'm trying to look at this divergence, so in a way, just like how different, right, things are. Because ultimately, what we're trying to do is that I'm trying to use QX, okay? As you can see, I have my PX and a QX, okay? So what I'm trying to do is I'm trying to use QX to approximate PX, okay? So PX is something that I don't know, I'm trying to find, and now I'm using QX, okay? So the high-level thing, of course, if you're trying to approximate, then of course, like a smaller divergence means that you actually good approximation, right? Okay, so this is just illustration. Like, so for example, if you have like a Gaussian distribution, okay, that's a PX, and then you're trying to say, okay, can I approximate? I want to basically find the parameter so that I can match in a way, approximate, right? QX, okay? So the KL divergence basically has a way of just showing like how or when or how much they're different, okay? And when they're different to what extent, okay? So if you try different, right, distributions, you will see that like when you have, of course, when you're further out, I don't know how easy it is for you to see the colors, right? So this is a blue one, this is a red is here, as you can see, right? This has a smaller area, a smaller divergence, okay? Because it's closer to the distribution I'm trying to capture, okay? So you don't need to memorize this, but I'm just saying there's another way, right? There are just different ways of measuring the similarity or distance of objects or distributions. Okay, so as you're working on some concrete problems, looking at your data, looking at the type of attributes you have, then you can search online. The textbook also has like quite some information, so you can work with the types of distance function or similarity function that's more appropriate for your problem. Okay. All right, so far I have talked about different types of data, different types of attributes, how you do some kind of statistical analysis of your data, okay, and how you measure similarity or distance, right? Okay, as I said, now we're going to start actually doing something with the data, like changing the data to some extent. Okay, so this gets to the data quality, data cleaning, integration, transformation, dimensionality reduction. So those are all steps in the kind of pre-processing like component. Okay, so this is when we take the data, right? Did some preliminary analysis, and now we're trying to transform or change the data in a way that is ready for my actual like modeling or some like prediction analysis. Okay, starting point. Why do we need to do pre-processing? Why can't I just take the raw data and use it? Right? So this really goes to the point of quality. Okay, so that's the fourth V when we're talking about the 3 Vs, 4 Vs, 5 Vs. Okay, that's the veracity. Okay, so that's about quality of your data. Okay, so nowadays, like for example, if you go to like Kaggle or some like some domains, they have actually more like a data set that everybody uses. It's clean, curated, it's nicely prepared. You can just apply whatever method you have on that data set, and you can compare and show how it's better or comparable to previous solutions. Okay, but a lot of or most of the real world data, they're not that easy to work with. They're messy in many ways. Okay, so that's why, like when you have your data set, right, you want to have some idea about the notion of the quality. Okay, how good your data is, and there are actually different measures when you're talking about data quality, right? Accuracy or like preciseness, like depending on like for example, if you're using a miniature sensors versus a higher end instrument, right? You may be getting different precisions. Okay. Or completeness, right? That's basically, okay, do you have everything you need? Sometimes you don't, okay? Consistency, okay, similarly, this is related to, okay, you may have, say, this value is good, but then like over time, like there or like across different measurements, you get inconsistent information. Timeliness is also important, right? Because sometimes, okay, I care less because once I have the data, I have it, right? But sometimes you really need the more recent data or how quickly you get the data. Because some of the like tasks are like like either real time or near real time, or if you want to like, for example, we had a discussion about the job market this year, right? So apparently you need more recent information so you know what's happening instead of using maybe 2 years back because things may be changing, right? The believability is a bit kind of subjective, but a lot of times it's based on like who produced it, the data. So it's more like in a way it's kind of like credibility, okay, of the source. Okay, so that's why I see different organizations, they may like some of them, they really like carefully document what they're doing, how they're getting the data, how they're doing any pruning or cleaning. So you actually know you have some way of kind of like, say, do I trust the data being good or not? Okay. Interpretability, that's also important. That's also associated with the metadata. I think we mentioned it during the first lecture, right? So it's about if you get your data, like somebody give you a data set, right, with say millions of objects and with say 100 dimensions. Okay, do you even know what you have, right? You're looking at the rows of data with the values, but you don't know what they are. That's probably not very helpful, right? So that's why I say when you're getting the data, make sure you understand, right? You have the corresponding like metadata or semantics, so you understand the data, okay? Accessibility, that's, I keep reminding people about like, when you think about course project, whether you get the data or not, right? Sometimes you just don't have the data, or you don't have one critical part of the data that would really like prevent you from doing anything that you may want to do. Okay, so all those are different measures, and they may be of different importance, depending on your problem setting. But those are all important aspects for you to consider, right? When you're trying to like leverage certain types of data for your project. All right, so we say there are issues, right, in terms of data quality. So either say, okay, oh, the data is bad, I cannot use it at all, but many times we try to clean it, right, so that it's still usable to some extent, okay? So data cleaning will try to address quite a few issues in the data. Integration is also very helpful. That's when you can take different data sets and try to combine them so you can grab more information, right? Also transformation, right, this is when you change your data in a way. Sorry, I mean, I keep hearing this beeping. If somebody can check your phone, looks like it's more like a messaging thing. Okay, so transformation, that's like when you, again, change your data in a way such that it's easier to work with, okay? Reduction, we'll talk about that later, right? So many times we want more data, but many times it's also useful for you to consider how you can reduce your data so you're more efficient and more effective. Okay, so let's go through this, okay? Cleaning. First question, right? Let's not jump into cleaning yet because you need to understand like why we need to do it, and then you have the right way to do it, okay? So think about the cleaning. This really comes from a real world data, and we know it's not perfect, or many times it's imperfect in many ways, okay? So how often, like why you may have issues in your data? Think about how you would collect data. Like I may do a survey with a class with some questions, okay? So I may not get like enough answers, right? So I just don't have, like not everybody are like say required, even I'm required, I may still not get enough information. So if you're doing some kind of data collection in the real world, right, starting point is you just don't have, right, all the data you need, ideally, okay? And then you may have just like missing values, and sometimes people just, oh, I forgot. Or the sensor just went out, right? You just don't have any readings during that time point, okay? And then like it could be just human error or instrument error, or during the transformation something happened, right? All those could occur, and then you may end up with missing value or incomplete data. Noisy data is so typical, right? Sometimes it's easy to see, right? If you just plot your data, you see like I expect a more clean line or clean curve, and then you see data jumping up and down. That's basically one way of saying it's noisy, right? And sometimes it's easy. This one's easy, right? Salary is a -10. Okay, so it's by general semantic definition that cannot be true, so this could be just an error, but sometimes it's subtle, more subtle than that. It's harder to detect that. Inconsistency. So this is related to noisy data, right? So the idea is that I have values, and individually they look okay, right? So like here, I think my example, yeah, age being 21, and I have a birth date, which also look reasonable. But when you see that this is a same person, then that's the inconsistency you can detect, right? So this cannot be, because there's some kind of relationship between those attributes, okay? And when look at it together, they're not consistent. Okay, so there are those scenarios, right? And we said that there are all kinds of things that may lead to some data quality issues, okay? Of course, we try to reduce or prevent those, okay? And things have really improved a lot, right, since the earlier days, because as more people starting to look at the data, we find issues, and we try to implement like better ways or more better mechanisms, right, so that we have better data. But still, there's still issues, okay? So this is probably just a question for you as you start looking at the data for your projects, okay? Like, we'll have some discussion, right? Discussing your report and your presentation, you can talk about how good or how bad your data is, okay? All right, so we have all these issues. Oh, actually, another note about inconsistent data. This is actually interesting because things may change over time. Remember, most of the data sets we'll be working with are collected over a longer time period, or some are like from a long time ago, or things have changed over time. So what was okay before now may have been different, right? So those are the things that you should all just keep in mind, and not just say, okay, I got a good quality data set, which was from, say, 5 years ago, and now I'm trying to combine it with another data set that's more recent, and there may be issues, okay? All right, so I hope this really kind of like would be stick in your mind is whenever you're working with data, okay? Because if you say no quality data mining results, another way to put it like garbage in, garbage out, right? Because ultimately, what do you put into your black box? You spend all the effort in your black box. If the data is bad to start with, sorry, that effort, right? Maybe wasted, and even worse, you may be coming up with like incorrect models or incorrect patterns, right? Okay, so let's try to handle it, okay? First one, when you have missing data, what do? If you check your data set, you see quite a few entries in your data set are missing, like empty. What can you do? Sorry, that one first. Okay, so you could replace with a mean value, okay? Even a simpler case, I can just ignore. Like if you say out of my, say, millions of rows, I'm missing some, it's a small percentage, I can probably just remove, right? If it's small percentage, I'm fine. Because in a way, I would say, like with data mining, many times I'll look at the general patterns, okay? So if the percentage is small and where you're missing the values are like relatively not like critical, you can just ignore it. Right? Okay? So that's actually easy. Right? You may think it's like, why would I do that? But if you have a reason for that, it's actually an easy way to do it. And that's actually done in practice often. Okay? Ignore it. And then, I can try to put in some mean, right? So mean is already better. There was actually another way, just I can put in some kind of global default value. Say 0. Is 0 always good? Do your reasoning, right? There was one extreme instance they're talking about, like, these are coordinates for the airplane. So if you're missing your coordinate value for your airplane and you just put in 0, 0, you're probably in big trouble, right? So again, those things are like, say, may seems simple, like say default to 0 seems to be reasonable, but do your reasoning. That's why, again, it's important to understand what kind of data you're dealing with, what kind of attributes you're dealing with, what kind of values do you expect to see. But when you have that, then mean, right? Mean value is reasonable, okay? So for example, I'm using annual income, right? I have an annual income attribute. Maybe if I'm missing a value, I just use a mean value. That's probably fine, because it probably will not skew my data one way or the other, right? But if I'm trying to compare different populations and look at the annual income, okay? So you may have like lower income group, you have a higher income group, okay? Their mean values can be quite different, right? So for me, just use a global mean may not be good. In this case, then you actually can be a little bit more refined. So you can see, okay, I'm trying to identify different groups. Now I'm missing some value for this group member, but knowing which group this data point belongs to, right? Then I can try to do a little bit more kind of refined estimation, okay? So I'll give you a few of those. So those are the kind of like process you can do, right? So ignore manual, automatic. I can use a global constant. I can use the attribute mean. I can use the attribute mean of the same class, right? So those are all like good ways to do it, right? Just make sure you reason about it, right? Why you're doing this and why this is a good way to do it. But then we actually learn like throughout the course, right? Some of the mechanisms or techniques we'll learn in this course can be used coming back to estimate some values, okay? Because later on we'll talk about the classification, we're talking about the prediction, we're talking about like outliers. All those actually would help us, okay? That's why it's an iterative process, right? So you may start with a data set with some missing values. You may remove the missing values for now, do your modeling, and then come back and say, okay, now I may see whether I can actually pull back some of the data I removed, because now I have a way of estimating or better estimation for those missing values. Okay? So regression, Bayesian inference, decision tree, these are all techniques will be covered later, later in this course, and you will see those can be used, right, to be for the pre-processing step. Okay, noisy data. Okay, so when you have noisy data, of course, many times you're trying to smooth things out, right? So you're trying to smooth things out, like binning is widely used. It's simple, right, and seems to have good results. So the high-level idea is that, okay, I know my data is noisy. Let me sort it, okay? And then I'm trying to just smooth out by those kind of buckets in a way, okay? So you put them into bins, okay? So within the bin, you can easily use the mean value, right? Or you can use look kind of like whether you're closer to the lower end or the higher end. So you have some way of pulling things together, okay? So after that, they look more similar, okay? So we don't need to get into the details, but a few more examples, okay? Regression, okay? So if you look at my plot here, it's a simple one, right? The dots are the actual values, the raw values, okay? And by doing that, I know they should somehow follow this line. So that's my linear regression, okay? So once I have that, then I have a way of kind of correcting or reducing some of the noises by using this regression line, okay? So basically I'm fitting the data into some kind of regression function. Oops, sorry, jump too quickly, okay? Clustering, again, this is a technique we'll learn later, but if you had a way of creating clusters, right, you can also identify points that are similar to each other, they belong to the same group, and then you can identify those outliers. And this is when you can just remove them, right? Because noisy data, if you say those are outliers which I don't care, once I identify those outliers, I can remove them. So my remaining data set is more coherent. All right, cleaning. So we talk about noisy, like missing data, noisy data. Those are some of the common like issues, okay? And we do have some way to address it, okay? Next, integration, right? So this is when you have not just one data set, okay? But you may have access to multiple data sets and you have you're trying to, right, integrate them, okay? So integration, of course, is useful in many ways. Just if I may have, yes?
Could you give an example of why you would try to integrate?
Yes, yeah. So why would I want to integrate data, right? One example on campus, if you may know, right, we actually have different databases of students, courses, faculty members, degree programs, okay? So that's, of course, like more kind of say, it's still related, but it makes sense if you're trying to pull out, say, the generalized either, say, faculty performance or student performance or degree program performance, right? So this actually makes sense for you to pull this information together, okay? That's a simple one. Another case, so this is actually in a research project, okay? So we are trying to look at ozone, okay? So we're trying to predict, like based on some kind of spatial temporal pattern, and trying to predict the ozone values, levels, concentration levels for the next day or two, okay? So this is generally to air quality, right? So of course you can use the air quality monitoring data, okay? So that can be ozone specific. You can also get, say, temperature, humidity, relative humidity. You can get like NOx values. So those are related, right? Air pollutants, okay? So you can pull this together. And even beyond that, knowing that ozone is actually a big part related to transportation, traffic, okay? So now you actually get to the traffic networks. We also pull in some vehicle data because we have like vehicle idling data set. Okay, and also we get another from Google Maps. We got, let's say, land of use, point of interest. So you know for any location, not only just there's a like coordinate, you actually know, oh, there's actually a materials like factory here. This is a rental car company, and this is a park. Okay, so as you can see, these all come from different data sets. They have different information, right? And they may be created for different purposes. But the fact that you know they're related for your project, what I mean, because they all can provide some information. Okay, so you can start thinking about other scenario. But many of the projects, when you start looking at your problem, you ask a question about what data sets I can leverage. Okay, all right, so I want to combine, right? So there's like, say, some like use in terms of combining. But when you're combining things, how do you link them together, right? Because the data set, they're designed differently, right? In our student campus, and that's actually probably easier because we probably have, hopefully, the same identifiers, right? If we say the student ID is unique in the system, right? Or the course IDs, or the faculties, like employee ID. So that may still give you a good way to identify them and be able to link them through different data sets, right? So this is related to the entity identification, right? The easiest case that they're unique and you know they're defined like in the same way, so you can link them directly together. But many times they're not like that, right? So what was the example? Yeah, student ID versus student number, right? They may be the same thing, they may not be. So that's again going back to the metadata like interpretability part. You have the data sets, but make sure you understand exactly what they are, right? So there's some kind of manual process, and there's actually a lot of more the automated way of trying to identify attributes that are either the same or they're related, okay? And this also goes back to the question about when you are integrating, right? How do you know they are unique, they're the same, or there's redundant data, Okay, so this actually goes back to our like correlation analysis, right? We mentioned this earlier when we we're talking about like just like talk about objects and how you can look at that. So here, just a quick info. I mentioned earlier that two lectures before, one lecture before. So this is more like a chi-square table. Okay, remember we did the calculations, right, of the chi-square values, and then we say, oh, when it's above 10 or a value that is larger than 10, we think it's like correlated. Okay, why? So if you want to read into it, right? So correlation coefficient, that's for numerical data. If you calculate, you get a value of like negative to positive correlation. So that's between -1 and +1. But for chi-square values, because it's basically you're summing the square, right, of the differences. So it's always a non-negative value, but that can be big. Okay. So what we want is that we're using this table, we should basically correspond to the significance levels, okay? So the link I post in Canvas actually has more description, okay? Like they actually describe this more, so you can learn more about the whole process. But here, as just a quick table reference, in our case, there's a degree of freedom which corresponds to the C and the R. So C is the number of variables you're comparing, and C is for one variable, how many values you could have. R is for the other variable, how many you could have. So for example, like we're using the, what's it like fiction or not, play chess or not. That's binary. So it's 2, 2, right? So if it's 2, 2, then you get 1 times 1. So your degree of freedom is 1. And if you have a degree of freedom 1, and then if you go all the way to, I think it's this one, this 0, 0, 1, so that's basically 1%, right? So that's a very small probability. And if you have a value above 10, so last time I think you remember got a value of 500 something, right? And that is when we say, okay, when it's above 10, it is significant. So it's above the significance threshold, so that means it's unlikely to happen by chance. So they're correlated. Okay, so also related to that, correlation versus causality, if you still remember the examples, okay? So we're doing some calculation practice with this, but at a high level, correlation analysis allows, especially for integration, it allows us to identify attributes that are correlated, right? So if they're like say, either the same or they are related in some way, then you can actually identify that in an automated way when you calculate the correlation coefficient, if it's a numerical value, or if it's a category value, you can use chi-square analysis to determine potential correlation among those attributes. Okay, so that's integration. Transformation, I know we're going through like quite a few of items here, but all those, I say, those are like kind of steps. You probably need to go through anyway. And as you're going through this, either say, oh, I'm not integrating things, so I don't care about integration. Or, my data is good quality, I checked, I'm good. But then you realize that you need to do all those kind of checks, right, to see whether there are issues and what you can do to improve it, okay? Now, transformation, what do we do here? So the name suggests, right here we're changing the data to some extent, okay? There are a lot of things you can do, okay, in this step, okay? So you're basically transforming your data so your data is usable or ready for whatever analysis you want to do, okay? Smoothing, that's actually related to the noisy data thing, right? So generally you want to do some smoothing so your data is good or like better, so you can actually see the patterns better, okay? Then there are the other two notions are related. So aggregation versus generalization, okay? So you can aggregate things. For example, like I may have the transactions, right? Credit card transactions across different branches. I can aggregate. So I can take, say I have 10 branches, right? I can aggregate them together, okay? So I have the total sales. Or I can aggregate that by customers. For example, like customer come in, they did actually say weekly purchases, and then I have a way of taking all that together, and I have per, like one combined aggregated transaction per customer, okay? So as you can see, right, when you're aggregating, apparently you're reducing the number of data points, right? Because you're taking multiple and combining into one, okay? But if it's a generalization, this is the one-to-one mapping. Okay, so for example, like all of us, right? If you look at our home address, right? There's street number, there's a street name, there's like which city you're coming from, which state you're coming from, which country you've come from. But if I'm doing my analysis, I care less about, let's say, maybe if I look at the street numbers or street names, it may not be as useful, but I care more about which city, which state, which country you're from, okay? So I take each object and map it to a higher level value, okay? So basically, let's say, okay, I take your home address, I just look at your country, right? Okay? Or like say I take all the individual detailed student information, now I only care like say which degree program are you in, right? But in this case, we're not reducing the number of data points, right? If I start with say 1,000 students, I would still have 1,000 students. It's just that the attribute values are generalized. Make sense? Okay. And then you can actually construct new attributes or features, okay? That's important or useful, right? So sometimes you can already take some calculation. I don't know how many do tax, or maybe not. If you do tax returns, there's a lot of calculation. You take A and a B, multiplying something, subtraction, or adding something. So as you can see, right, then you will have a new attribute, okay? It's different, but related to what you had, okay? And for example, like if I take my, like say, image data, right? So earlier days, right, we will take image data, we have the individual pixel values, and then we will be able to use that to calculate some kind of color distribution. Right? What's the distribution of the color within this image? So instead of the individual pixel values, I now have just one vector representing the color distribution. Right? That's a new attribute. And then normalization, discretization. So those are things actually are heavily used. Why do we want to do it? Okay. Think about, like, again, a data set with employees, right? You have their age information, you have their annual income information. What's the range for age, your employees? 20 to 60, maybe 70, that's about it, right? What's the range for annual income? Tens of thousands, hundreds of thousands, right? So if you take those two together, remember our distance calculations, right? If we're combining them together, so you have a value of, say, 30 here, and then you have a value of 50,000 there. And then you say, okay, if you combine them, right? One, you don't have a good notion of like what does it mean if you have a value of 30, right? And second, if you combine this together, like one value may throw off your calculation because that's dominating. Okay, so normalization is a way to normalize the range to some extent so that you can, right, across different attributes, across the different distributions, they're more comparable. Make sense? All right, so there are a few things to do, right? So the first one is min-max normalization. So that's simple. So I take my original mean, and I want to just map it to a new range. Okay, so new range could be 0, 1, or 0 to 100, or something. Okay, but once everybody's mapped to the same range, then it's easy comparable, right? Okay, so here my example, right, I have my income range, which is 12,000 and 98,000. If I normalize to 0 and 1, right? So what I need to do is basically take this difference, right? That's the original range, okay, and scale it based on the new range, okay? So if you had like original have a value of 70,000, 73,000, basically you minus the, that's the mean value, right? And then scale it up based on the new value, you get a value of 0.016. Now it makes sense, right? Earlier, when we just give you a value of 70,000, you don't really know where this point lies within your overall distribution, right? But now with the normalization, I know it's between 0 and 1. And I have a value of 0.7. So you know roughly, right, where this data point is. You see what I mean? Right? So this is the kind of the idea or the benefit of like normalization. So everything is kind of mapped to the same scale. So it's easier to understand each point where they are and then compare, right, different points where things are. So if you're like trying to look at different like potential job offers, right, same thing, right? So if you had a way of mapping, right, normalize, you say, okay, for this particular offer, I would be around maybe 50th percentile. Another one is kind of 30th percentile. Then you can probably kind of compare, right? It's better, like more direct comparison. Another one, instead of doing 0, 1 or min max, I want to do a bit of kind of distribution because a lot of times in the real world you see some kind of normal distribution, okay? So now we're using this kind of z-score. So you have a 0 point, right, which is really the middle point. So it's like if you add a 0, that means you're right around the middle, okay? Up or left, then it's either below or above. Yes?
So would the min-max keep the same sort of shape of the data?
So with the min-max, can I do the same kind of shape of data? Potentially, right? Because if you do, for example, from 0 to 1, you can see if it's 0.5, it's roughly there, but that's assuming a normal distribution. But if you had a skewed distribution, you map it, you would still get a 0, 1, but then now you don't know exactly. So the 0.5 value may or may not be your middle point. Does it make sense? While with the second one, I assume it's a normal distribution, okay? So in this case, when I get 0, and then I have a way of calculating whether it's to the left or right, so this is basically 1 standard deviation out to the left or like 2 standard deviation to the right. So that'll give you a sense about how you compare to the middle, okay? So same thing, if I take the original value, 70,000 something, right, 73,000, right, and then I do the normalization, so I have my mean score, so that's the mean income is 54, okay? And now I have a standard deviation of 16,000, so you have basically a relative way of saying it's 1.225, so that means I'm a little bit more than 1 standard deviation out, right? Remember, if you had your 1 standard deviation left and right, that's 68%, right? And then if you have 2 standard deviation, that's 95, and then you have 99.7, right? So you kind of know where you lie within the overall distribution, okay? Right, so these are 2 kind of widely used normalization methods. One more, this was a bit more kind of, how to say, like rule of thumb kind of thing, right? You basically just approximate, right, to some decimal number, okay? So basically what you have is, like, for example, you have a range of this like 986 from negative to 917. So roughly, I'll say between negative 1,000 and positive 1,000, right? Okay, so if you do that, then that just gives you a way of say, okay, I turn that into negative 1, positive 1. So just give you, again, a range between these two. So you have a notion of where things lie for that particular point, and then you can compare across points. Okay, so normalization said like one is just very useful in terms of when you have very different attributes, very different attribute values. When you map to the same range, same distribution, then it's easier for you to compare, okay? All right, discretization. Okay, so as the name suggests, right, when you have a numerical value, and they're continuous, right? So for example, like I have like earlier, yeah, so again, using my annual income information. It's a continuous value, right? Sometimes you get to like integer value, sometimes you get a 0.27, whatever. So some like get to the digits, okay? Or if I'm doing measurements, right? The satellite, if I'm measuring temperature, I'm measuring like wind speed, or not measuring, the stock price, right? So those are all continuous value, okay? Why can't I just use the continuous value directly? It's useful, right? Of course, like you can do, say, the comparison. But a lot of times you want to put them into buckets or groups, right? Because we're looking for similar patterns and compare, right? So the individual value, for example, like 100.72 versus 100.9, they're probably similar enough, and I want to put them into one because that's actually helpful when you're looking for common. Like remember, we're using the like frequency, right? The mode is talking about the most frequent values. Okay, so if you had a continuous value, the mode may not be very meaningful because you have things that are related, similar, but they're just not the same. So you cannot find it, right? So discretization basically just trying to group them, and they use the same value, right, within that group. Okay, with numerical value, as I said, like we can basically take this continuous range, put them into intervals. Okay. And once like, you have within the same interval, then this interval value or label, right, is used for the whole group, okay? And with that, then actually it's easier. We'll see down the road, right? When you have those discretized value instead of the like original, like precise numerical values, then it's easier for you to find similar patterns and compare across different patterns. So how do you do it? Right? You have a range. You sort things together. You got this continuous range. You have the values. Okay. So there can be supervised versus unsupervised way, split or merge. Right? As the name suggests, if it's like supervised, meaning that I have some way of telling you, okay, these should be together, right? Those should be here, or something like that. If it's unsupervised, okay, it's like I don't give you any hint. Just say, okay, these are the values. Take it and do whatever you can. Put them into different buckets, right? And then split versus merge, right? As the name suggests, if I'm splitting, that means I take the whole thing as like one bucket. I keep dividing it. So I have smaller and smaller buckets, right? And if it's merging, I start with individual values, keep merging things. So I get bigger buckets and stop somewhere. All right? Of course, how do we do it, right? Binning, we talked about it earlier, right? So binning it's basically splitting, right? You take the whole thing. Remember, we sort it, put it into different bins, okay? It's unsupervised because I just take the sorted value and just use some kind of bin to do it, right? Nobody's telling me that this should go to this bin, this should go to the other bin, right? Histograms, right? That's a visual display we showed earlier. So if you want to take histograms, then you can actually also have a very good way of seeing where things should naturally fall together, where there's a gap, so they should be separated, right? Cluster analysis, same thing. If you have a way of putting those points into clusters, now within cluster, they are naturally considered similar, right? And that's the label or discretized value you can use maybe as a mean or as the most frequent thing within that cluster. And now you have a way of separating clusters. Okay, they're also entropy-based. We'll talk about entropy later, so don't worry about that. Like, we're not getting all the details right now. They're also using chi-square. You see, like, chi-square is actually used across different things. But all those, like I said, the idea is you're trying to find similarity versus the differences. Okay, we're just using it differently. Okay, I think I had a intuitive partitioning that I'll skip. So next one, data reduction. Yes. So this is when we say, okay, we have data, we cleaned it, we can integrate, we can do various kind of transformations, but why do we even consider reducing our data sets? Okay. One, when your data set gets too big, it's hard, right? I say it's much easier to work with, say, 1 million data points versus 1 billion data points. It's much easier to work with 10 dimensions, 10 attributes versus 100 attributes, right? Okay. So when you know that you have a lot of data, and if you have a reasoning, because that's the important part, you don't want to just be, how to say, oh, I have too big a data set, I want to just cut it in half, or I want to take it 10%. You need to be careful how you do this, right? You cannot just throw away data. But different data points, they carry different amount of information, right? So your goal is to reduce your data set so it's more efficient to manage, to work with, while still giving you similar results. Meaning that you don't want to be removing data. As a result, your patterns will be skewed or not representative of the bigger data set. Okay? So that's what I want to do. How are we going to do it? What will be something that comes to your mind? If you have a data set that's too big, what can you do? So think about data as data points, objects, right? And dimensions. So you can either reduce the number of objects, right? So instead of, say, 10 million, I can do 100K. So you're basically choosing data points to remove, okay? Or out of all the dimensions, right? I have, say, 100 attributes. I don't need all that. So I can remove the ones that are not as important, right? That's the idea, okay? So that's why we typically refer to as the two types of reduction, okay? One is numerosity reduction, the other one is dimensionality, okay? So one side is I'm reducing the rows, objects, number of objects, right? Another one is I'm reducing the columns, the attributes, dimensions, Okay, and there are different ways. So let's look at a few examples. Okay, so the here is that okay, I know I have too many data points. Okay, I want to reduce some. So there is one that's like parametric. So basically the idea is that if it's parametric, it means that you have some kind of distribution or some model. You're trying to fit your data. Okay? So once you have that, then you only use the parameters, right? So if you have, say, I know my distribution is a linear distribution, then I only need a few parameter values to fit the whole thing, right? But or if it's non-parametric, of course, then in this case you don't have a model, so you need your data to tell you how you can remove things. Okay, so let's look at a few examples. Right, again, regression. Regression is actually widely used in data mining because regression can help you identify patterns, remove noisy data, right? Reduce the data that you need to maintain. So similar things is this one, like I have the individual data points which may be huge. Okay, but if I say based on my analysis and somehow realize that this data really is follow a certain distribution, right? So so instead of like using the individual data points, I only need to know this line, and to know that line, how many parameters do I need? The slope and the offset, right? 2. This is the linear one, of course, right? If you have like say, a polynomial, like a regression or log linear, they have a few more, but still you're talking about a few parameters instead of many, okay? So of course the reasoning is that is your data set actually following a good distribution, or is the model, the regression function is a good fit, right? Are you still keeping the key information in your data set by using those models, okay? So regression. Data cube aggregation, okay? So this is actually related to the aggregation we'll talk about earlier, okay? But with the data cube, the general idea is just that you have many dimensions, right? And you can aggregate along different dimensions, okay? So using our a branch, what was my, so say my original data, right? I had say which year it is, and then we have so the different types information. I have different branches, right? Okay, so if I care less about the individual branches, I can combine, right? I aggregate along the branches, so it's the total, okay? So if I do that, then I would have only say by which year and then which quarter I have the cells. So I only have so instead of say if I have 10 branches, you basically taking every 10 value into 1, right? That's how you're reducing it. But again, reason about why you're aggregating along that dimension. Because if you care about the branch level performance, then you wouldn't be aggregating along branches. But maybe you're aggregating along different quarters, right? So maybe I care less about the quarters, but it's more about the combined cells, right, across branches. Okay, and sometimes, but if you want to look at the regional, the seasonal, dynamics, then you don't want to be aggregating along the time, because which month or even which week or which weekday can give you more information. Okay, so the high level thing is that okay, you can aggregate along different dimensions, but you need to be doing the reasoning about why I'm aggregating on this and why this would still be fine for the mining task I'm trying to do. Make sense? Or you can if you say, I don't know, but maybe I can aggregate along different dimensions. I try different approaches. So you basically have different branches. Sorry, different routes, you have different subsets you're working with, but each one is now smaller. So it's more easier, more efficient to handle, okay? So that's aggregation. Histograms, we talked about earlier, right? So when you have a way of defining your data into buckets, right? And then now you have a way of saying, okay, maybe within each bucket, I don't need everybody. I need some of those, right? So you can partition this, and after that, all you need to remember is the buckets, right? This is the bucket, and how big or what's the frequency within that bucket. And then, so again, instead of the individual data points that we fall within each bucket, you have 2 values. It's basically each bucket you have 1 value to represent the whole bucket. Okay. Clustering, I mentioned it earlier, so we'll not get into all the detail. But another thing I would like to mention, sampling, right? All of you have heard about the term sampling. If you take the probability course, you know sampling is something we do all the time. Okay, easiest one, random sampling. So randomly, right? So like say I'm doing a random sample, say 10%. So I'm taking a whole data set, I randomly pick 10% of it. Is that good? Why not? Some of you are shaking your head. Why not? When this may not be a good idea. If I'm just doing a random sampling. Yes? Your data set may be skewed, right? Because so like say, if you take your raw data set, say if I do a random sampling, if you have some skewed distribution, you may be sampling unevenly to some extent. As a result, you may have a skewed representation of the data points. Okay? There's another one. You may have heard about this with or without a replacement. Okay, this again depends on your actual semantics, right? The process is slightly different, right? Once you sample, do you put it back or not? Okay, and that actually will give you a slightly different results. Okay, another one related to the cluster or stratified sampling. So that means instead of a random sample, I want to have some idea of the clusters or groups, so that when I do the sample, I sample relative to the distribution of those clusters. For example, like say if I had a class, right, say like if it's a half-half, undergraduate students, graduate students, I do a random sample, it's probably okay, right? But I had like say, if I know I'm looking at like a smaller like percentage of undergraduate students versus a higher percentage of say graduate, and maybe I'm separating masters versus PhD, then my sampling want to respect that distribution. Make sense? Again, this is a process. Like you can do this differently, but just make sure you reason about your process and why that is okay or not for your process. Okay, we're almost there. So one last point, dimensionality reduction. Right? We said that if you want to reduce your data point, your data set, either you reduce the number of objects, number of rows, or dimensions. Okay. There are a few things to do that, right? So either just say, okay, I take the existing dimensions, I identify ones that are more important, so I keep those, so I keep selecting ones that are more important. Or I can say, I keep removing things that are not helpful, right? For example, if you take one dimension and say, okay, everybody is from CU, then that dimension doesn't help you, right? Because that doesn't help you to differentiate one way or the other. You can remove it. Right? So you have some way of say in terms of the selecting, right, the attributes that are more important. Okay? So you can do this either bottom up or top down. As I said, either you keep removing things or you keep selecting things or adding things. Okay? But you need a notion, right, to measure how important like this particular attributes are. So you can compare, like I want to keep this one but remove that one. Okay? We'll get into some of the details later, okay? Another one, this is actually transformation. So in this case, I'm not just taking dimensions and just remove. I'm actually changing, okay? I'm changing my dimensions, okay? So some of you may have heard like Fourier transform, wavelet transform. So the high-level idea is that you are taking our original space through some kind of transformation, you change it to another space, okay? And in that process, the idea is that you may be able to kind of like, how to say, identify the signals that are more important. Okay, so here I'm using wavelet, like discrete wavelet transformation, okay? So the high-level idea is that, okay, instead of the individual pixels of the raw images, okay, I'm trying to use those wavelets. So those are called wavelets, okay? So the wavelets are actually signals, right, of different patterns, all right? When you do this transformation, what do you get are those coefficients. So the coefficient is, okay, how significant you see those pattern, this wavelet in your signal. Because your original data is being transformed into some kind of linear combination of your wavelets, okay? So now those coefficients actually give you an idea about which signals are more important in your data set, okay? So this is the example of using like discrete wavelet transformation for image compression. Actually, later they're using it for similarity search, okay? So The original image is, I don't have the original one. This is using 16,000 coefficients. You can see it's a pretty good, right, representation. Later on, as you reduce, it gets fuzzy. But it turns out, actually, if you only need, like, I think in their experiment, they say 100 coefficients can already help you identify similar images. You don't need all the information, right? It's not, of course, it's not as precise as the original one, but you have enough of the strong signals to help you to identify similar versus different images, okay? All right, it's that time. I have actually a couple slides. I'll finish it next time. Reminder, homework 1 is out. It's due before next Thursday class, okay? Check it out.